So for the most part of this chapter, we've dealt with statics, which is charges not moving. But we can do problems. Can't spell, sorry. We can do problems using statics for velocities much less than the speed of light, which is 3 times 10 to the 8th meters per second. So if we think about the biggest thing that we've talked about is the force. And the force can be represented electrically as the charge times the electric field. And mechanically, it would be the mass times the acceleration. And rotationally, it's the mass times the velocity squared over the radius. All of these all are equal. So we can convert from one system to another. And let's see how we can do that with a problem. So we have an electron moving to the right at 7.5 times 10 to the 5th meters per second, enters a uniform electric field parallel to its direction of motion. If the electron is to be brought to rest in the space of 4 centimeters, what direction is required for the electric field, and what is the strength of the electric field? So for part A, we can say that electrons will travel opposite the direction of the electric field. So to stop the electron, the field must be in the same direction as the electron travels. Okay, so it has to be going to the right also. Now, let's see what we're given here. We know that our initial velocity, v0, is equal to 7.5 times 10 to the 5th meters per second. We know that our charge is equal to the charge of an electron, and that's just equal to negative 1.6 times 10 to the minus 19th coulombs. Our distance that we want the electron to travel to stop is 4 centimeters. And looking in the book, we can find the mass of the electron is equal to 9.11 times 10 to the minus 31 kilograms. Okay, so let's start by figuring out how we can solve this. Well, we're talking about velocities, and I know that V final I want to be equal to 0 meters per second. And I have no time. So from 215, we want to use the formula V final squared is equal to V naught squared plus 2 times acceleration times delta x. You should be familiar with this formula, basic description of motion. I know V final, I know V initial, I know the distance, delta x. I don't know the acceleration. This is what I need to find. So I know the mass of an electron times its acceleration is equal to, this is just a force, is equal to its charge times the electric field. So that means that the acceleration is equal to charge times electric field divided by the mass of an electron. And now I can substitute, and I know V final needs to be 0. Substitute in, and the electric field is what I'm interested in, so I need to solve for that. So I'm going to get E is equal to negative mass of the electron times VO squared over 2Q times delta x. Putting in our values, it's negative 1.6 times 10 to the 19th, minus 19th. Did I put that up correctly up here? Yes, I did. Okay, minus 19th coulombs times 7.5 times 10 to the 5th meters per second squared divided by, oh, I put the wrong value in the top. It should be the mass. Sorry about that. Let's change this. This should be the mass, not the charge. And that was 9.11 times 10 minus 31st kilograms. That's better. Sorry about that. And now I can do my charge. So 2 times negative 1.6 times 10 to the minus 19th coulombs. and my distance is 4 centimeters, so 0.04 meters, and that gives me a total of 40.034 newtons per coulomb. So that's how we can use our ideas from 215 and particle motion to solve a simple problem with electrical parts or electrical characteristics.